Hello everyone, my name is Karan Mashru. Welcome to this video. So in this video, we are going to look at the solution of the problem, that is consecutive ones not allowed. First of all, let us start by understanding the question. What does question say? Given a positive integer n, count all possible distinct binary strings of length n such that there are no consecutive ones. So we have been given length n and we need to find how many binary strings, means strings containing zeros and ones are possible of length n such that there are no consecutive ones, means two ones should not be together. Okay, two ones, three ones, no, at least two ones should not be together. Okay, so even three ones are also consecutive ones. Output your answer modulo 10 to the power 9 plus 7. For example, if my length is 3, then there are 5 binary strings in which there are no two consecutive ones, that is 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 0 and 1, 0, 1. For n equals to 2, it is 3. You don't have to print answer or take inputs. Complete the function count string which takes integer n as the input parameters and returns a single integer denoting the answer. The expected time complexity is big O of n and expected auxiliary space also big O of n, and the constraints are given here. So now if we think about solving this problem, then what can be the brute force approach? The brute force approach could be to just try and recursively generate all the possible strings, and whenever we get a string where there are two consecutive ones, we do not count that. Okay, so we generate all the strings in which there are no two consecutive ones and return the count of the number of generated strings. Now recursively, if we try and generate all the strings, if there are n number of positions, at every position there are two choices, either 0 or 1, right? So for all the n places there are two choices. So the total number of strings generated is 2 to the power n, right, which is exponential. So this will give us time limit exceeded, and we need to think of something more efficient. Okay, so now let's try and do one thing. Let's generate the number of strings in which there are no two consecutive ones for some small values of n, and let us see if we can get some pattern. Okay, so for n equals to 1, there will be two possible binary strings in which there are no two consecutive ones, that is 0 and 1. For n equals to 2, we have 0, 0, 0, 1 and 1, 0, right? There will be three possible binary strings because 1, 1 has two consecutive strings. For n equals to 3, we will have 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1 and 1, 0, 0. Okay, so there will be 5 such strings. Okay, for n equals to 4, we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, right? So this many are possible: 1, 2, 3, 4, 5, 6, 7 and 8. So for n equals to 1, the answer is 2. For n equals to 2, the answer is 3. For n equals to 3, the answer is 5. And for n equals to 4, the answer is 8. Can we see some pattern here? For n equals to 3 onwards, number of values possible is nothing but the sum of previous two values. For n equals to 3, the answer is 5, which is nothing but 3 plus 2. For n equals to 4, answer is 8, which is nothing but 5 plus 3, and so on. You can observe. For n equals to 5, you will get 13 total possible strings. Okay, so how can we do this? We can simply say dp, we can take one dp table. What dynamic programming I am saying? Because here solutions to smaller problems are used. First of all, we are converting this recursion into the polynomial, and solutions to smaller problems are used to solve the bigger problem. So I will take one dp table of size n plus 1, and I will say dp1 is equals to 2, dp2 is equals to 3, and for I equals to 3 to n, dp of I is equals to dp of I minus 1 plus dp of I minus 2. Okay, and at the every step I will say modulo mod, right? Because we have been said that take modulo 10 to the power 9 plus 7. So I will calculate this dp table. What does it indicate? dp of I indicates number of possible binary strings of length I where there will be no two consecutive ones. And finally I will return what? dp of n, right? So now let's look at its actual implementation. So if we look at the actual implementation, so I have been given n in the input and I have taken mod equals to 10 to the power 9 plus 7. I have taken one dp table. I have initialized these two base values and for 3 onwards I have made this relation, and finally I have written dp of n. What will be the time complexity? It will be big O of n because I am running a for loop of size n. What will be the auxiliary space? The auxiliary space occupied here will also be equal to big O of n. Why? Because I am taking a dp table of size n. Now let's submit this code. So let's submit it. Okay, so we have solved this question successfully. I hope you have understood the solution completely. Thank you.